So if we start on question 2. So the first thing, I would always copy out the diagram, okay, and it helps as I read through, I'm just going to say, the fixed point A is vertically above the fixed point B. Okay, a light inextensible string of length 5.4 meters. So there we go. Has one end attached to A and the other end attached to B. The string passes through a smooth ring. Okay, what are the implications of through a smooth ring?
Same tension.
It's the same tension on either side. So there's a tension there and there's a tension there, and that caused at least one person some grief, just that little thing there. Let's say that's 3.4 and that's 2 and that comes to 5.4, so we've used that bit of information. The string passes through a smooth ring of mass 0.24, so this has got some mass, so 0.24 G is my force down on it, and R, this is R, the ring, is moving at a constant angular speed in a horizontal circle. 1.6, and it's moving in a horizontal circle with constant angular speed, so we're going to call that omega, in a horizontal circle. The circle has radius 1.6 meters. Okay, we can see that. AR is 3.4 and RB is 2, as shown in the figure. Okay, that process of just reading through the question, yeah, that's how we can start. Now we can start thinking, find the tension in the string. Part 1. So we're going to consider the forces. Basically, we've got F equals ma, and that's pretty much all we've got. Okay, so F equals ma. Let's consider it in the vertical direction. Because we don't know about the horizontal direction because of the omega, but that's presumably what the next part is going to be. So vertically, let's call this my positive direction is up. So I've got TR. Okay, what do I need now? I need some angles. Okay, this was a pain to mark, but if we put an angle in here, I'm going to define it there, and I'm going to define this one there. But you could have put your angles in a different place, and so you might not have exactly the same thing. But do check that you've got it right, because I think there were a few mistakes with the angles. Somebody used tan, which was bad. Was it on this question, or was it another question? It was this question. Okay, so we want vertically, that's going to be sine theta positive minus t sine alpha minus 0.24 g equals 0. Yeah?
So I take the angle, I do the line between A and B and the angle.
You took the line between A and B, and you took the angle up here.
Yeah.
Yep, that's fine. That still will be sine because your right angle is here. Yeah, and therefore 3.4 is still your hypotenuse.
No, the angle.
That's not a right angle at R.
ABR.
ABR, the right angle is not at R. There's nothing in the question that says that's a right angle. Will that be your problem? Have you assumed there's a right angle there? Have you assumed there's a right angle here? Okay. Okay. I'll carry on. So what I'm going to do is I'm going to say I'm actually going to work out the length here because I'm going to use that in my my sine theta and my cos theta. So a bit of Pythagoras, root 3.4 squared minus 1.6 squared means that this length here is 3. And that's when you know you're onto something good, because you've got a nice number, and therefore you're kind of doing the right thing here. 1.2. So I now know that t sine theta, sine is 3 over 3.4, minus t, do you see how I've avoided going via angles? Sine is, and I know some of you were doing this, 1.2 over 2 minus 0.24 times, there was a 9.81 person, please use 9.8 in maths. Okay, so 3 divided by 3.4 minus 1.2 divided by 2 is 24/85 of t equals 0.24 times 9.8 is 0.0244, etc., divided by 24 divided by 85. And so t equals 17 over 196, which is I feel like I've made a mistake here. This should be 8.33. That doesn't look like 8.33 to me. 9.8 times 0.24 divided by 25 divided by 85. 8.33. Sorry. I think that's wrong. That's definitely wrong. 0.24 times 9.8 is 2.352. There we go. Okay. So then part 2, find the angular speed. What's the only thing we can do?
Do the cos thing?
F equals ma horizontally, and it's going to have causes in. So we're looking horizontally. So we know that the force towards the middle is t cos theta plus t sine alpha equals mv squared over r, or mr omega squared. Given that we want omega, let's do it in omega. Mr omega squared. We now know t, we know cos is going to be the adjacent, so that's 1.6 over 3.4 plus t times sine is, sorry, that's rubbish, cos alpha there. Notice how the coses and sines usually go together, and it's a way of just double checking that you're on the right track. So cos 1.6 over 2 equals the mass, which is 0.24, times the radius, which is there, times omega squared. Okay, t is 8.3. Just to save time, I'm just going to write down what omega is as a result of that. So omega equals 5.25. Somebody forgot to square root.
Yep.
Okay, but you've done all the hard work. Okay. Happy with that? Yeah. So, part B, totally new question. Okay, totally new and a part B that's totally different.
Yeah.
Yeah. It's basically they're only allowed to write 4 questions, but they've got more topics, so they. So part B, just got your head into that one. Now you've got to change gear. A particle of mass 0.3 kilograms is joined by a fixed point to a light, inextensible string of length 1.8 meters. The particle P moves without resistance in part of a vertical circle. Okay. So there's P, moves in a vertical circle. We're interested in the angle to the downward vertical, so I'm going to call that theta in my general case, and it's kind of moving around this way. We've got a tension there. We've got a weight 0.3 g. I'm just going to go through and read. String of length 1.8 meters. Without resistance, makes an angle of 25. Okay, so it gives you a specific case when OP makes an angle of 25 degrees with the downward vertical, the tension in the string is 15 newtons. What's the only thing you can do? F equals MA. Okay, F equals MA, so that's going to be my theta. So vertically, I can do this. So T cos theta minus 0.3 g equals 0 acceleration vertically. We know T is 15. We know the angle is 25.
So look at the speech and we do radial acceleration.
Yeah, that's what I did.
Yeah, this is interesting. Why is this?
Because is it like accelerating upwards or something?
Well, this is going to imply that this isn't 0, isn't it? Should we try that? So that would imply that it's 15, but you're right, this isn't where we're going. Minus 0.3 times 9.8.
No.
Oh yeah, it's moving in a vertical circle, isn't it? So it's accelerating in an upward direction. Okay. So what's the problem with what I've done? That's bad. Because
It's not moving at constant speed, so acceleration's not zero.
so acceleration is not 0. So how can we change this?
Using circular motion.
Okay, and what do we know? What direction are we therefore going to do F? Because we're still going to do F equals MA.
Long.
Yeah, we've got to do it along here or
Like
perpendicular. So which is the more useful one? Perpendicular, because what do you know about the perpendicular one?
NV squared over R.
Yep, and it's moving, and that tension there. So we've got F equals MA in direction of the string, in radial direction. So we've got T, and we've got theta. We've got T minus 0.3 g cos theta equals, do we want V or do we want, find the speed of P, so we want mv squared over r, which is 1.8. Yep. We know T is 15. 0.3 times 9.8. We know cos is 25. We know the mass is 0.3 v squared over 1.8. So v squared, well, let's just shorthand. V is then going to be 8.6 meters per second. Okay. Have we got time to quickly do part B before we finish? So part B, part 2. Find the tension in the string when it makes an angle of 60 with the upward vertical.
Conservation of energy.
Okay. Yep. You did it, but got it wrong. Okay. So energy.
I don't even know what word it is.
Okay, so can I just make comment on everyone's question here? It was really difficult to follow what you'd done with this question. This was one of those. Pardon?
I thought I used like nice letters.
You didn't use nice, but there wasn't any kind of. I could have spent with yours, Ollie. I could have spent a bit more time, and I could have probably worked it out. But it wasn't easy to follow, is what I'm saying, even with those nice letters. So energy at 25 degrees. Yeah, this would be my suggestion. I would take GPE to be 0 here, up at the top, okay, because although it's going to be negative, it's a fixed point that is easier to work about than the bottom. Okay, it's not. Yes, but it's a 2 calculation fixed point because you've got to do. If that's the bottom,
Can I do it from like when it's at 25?
you can, but that's even more difficult
Really?
because it's a subtraction. Because where it's going to end up is not then a nice thing in terms of this theta. It's not a nice expression in terms of theta. It works wherever you do it. It works. Okay, but if you haven't got the right answer, then you might want to think about an easier way of doing it. Okay, so energy at the start at 25. Well, we know V. So we've got a half m times 8.60 squared using the number you've got in the calculator. And our GPE is negative, but it's m, g, and my h is just 1.8 cos 25. Yeah. My energy at 60 degrees.
Wait, well, why is it?
Was it just
Why is
one
it just
point?
yeah? Why isn't it then plus at minus mg brackets 18 cos 25 plus 1.8 plus 1.8
Cos 60.
sine
Sine.
60.
Okay, I'm taking GPE to be 0 here. So I want the vertical distance down here. I want that.
You're just doing it separately.
I'm saying that I want the energy at the start here has 2 components. It has kinetic and gravitational, and I'm saying my GPE 0 here, so I can write then a simple formula for the GPE at this point. It's negative GPE because it's below this point, but this is 1.8. This distance is now, this is why I do it about here, is so that this is easy.
I thought doing it from the bottom was going to be easy.
It's rarely, because this is 1.8. You could do it from the bottom, but it's 1.8
As in like where
That would be
the
the point where it is at 25 degrees. Is 0.
there.
Yeah.
Okay, then you say that's 0, and then your change one is your different one.
Okay.
Yeah, it can get there,
Yeah.
but I'm trying to do the way that I think I make least mistakes with. Now, if you've got another way that you don't make mistakes with, use it. If you can see where quickly you've gone wrong, use it. All I'm trying to point is yours were difficult to follow.
Yes.
Yeah, and therefore, if you look at what I've done and compare it and think, could that have been... So I can now write down, without really thinking, mg times 1.8 cos 60.
Yep.
Yeah? I'm then going to equate those two and find out v.
It's really small.
Yeah, so
But how are they both negative?
because it's 60 degrees to the... Oh, sorry. Thank you. To the... I've got a different angle. Sorry, I misread that.
So should the one at 25 degrees be a...
This be... No, I'm going to call this 120. So my theta is consistent. This will then be a negative number, and so this one will be positive.
Okay.
Sorry, I misread that. That's my fault. Yeah. So you could call that positive. Another way of doing that would be say, here, that's positive. mg 1.8 cos 60.
Yeah.
Yeah, cos 60.
Why is it 120?
Because it's
Oh, no,
60
sorry,
off the...
yeah, no,
So I'm measuring it around there, and I'm letting cos sort out the negatives. Okay, but yes, you could do that a different way. But you're happy with where? But my point still remains that you can then just equate these. You can see that the m's go. I'm going to multiply it by 2 at the same time just to make my thing nice. So I've got 8.60 squared minus 2g times 1.8 cos 25 equals v squared. I'm not going to forget the 2 here, minus 2g times 1.8 cos 120. Rearrange, and I get v squared equals 24.4. And then I've got to go and get the tension. So I'm then going to, the final question is the tension, and we're running out of time. I think I'm going to pause it there and carry on, but I think you can probably finish that off. Okay, so we've got this particle that's moving around in a circle. So it's moving in this direction. We know what V is because we've used energy to do that, and it's now wanting us to find T. So we've looked at energy. We're now going to look at, and it's got a mass. Let's just remind ourselves what that is. 0.3 kilograms. And so we know that's our angle. Actually, I'm going to redraw this because we know that it's actually up there. And that's my V. That's my T. That's my 0.3 G. Down there, and then I know that this is my 60-degree angle. So I know that looking at F equals MA towards the centre of this circle, I know that towards the centre T plus 0.3 G cos 60 equals M V squared, which I know from up there, over R, which is still R 1.8. Okay, I rearrange sub V squared in, rearrange that, I get my T to 3 significant figures. It's 2.60 newtons. Okay, then it says part 3, find the speed of pitch at the instant when the string becomes slack. So this is effectively a reverse of the question that we've just done. We're going to use the same formula. We're going to call our theta, we're going to have it up here because I think that's slightly nicer. Now we're going to have GPE equal to 0 here, and then this is this theta. When it becomes slack, T equals 0. Okay, we've got 0.3 G here. And so what we know is we know that T plus 0.3 G cos theta equals 0.3 V squared over 1.8. And we know that T is 0. Okay, so that gives us one formula that gives us theta, the relationship between cos theta and V squared. But we also know that it's still true that the energy equation that we had at the beginning, so let's go and have a look at that. Yeah, so the energy at the start, which was our half M half M V squared, and that was, let's call that V1. Let's call this V2. Half M V1 squared minus M G H, which was 1.8 cos 25. And we know that V1 squared. And the energy when it goes slack is a half M V2 squared plus, because I'm going to use this new theta, mg 1.8 cos theta. And so we want the speed, so we want to eliminate cos theta. So we can see there from this equation at the top, we know that, oh, let's just go over here because we can. We know that (1.8) g cos theta is, because t is 0, the 0.3's cancel, is v2 squared. So I'm going to sub that into here, and I get, because these two equations are equal, I get half m v1 squared minus mg cos 25 equals a half m v2 squared, the v that I'm trying to work out, plus m 1.8 g cos theta v2 squared. Okay, m's all go. And I've actually got here 3 over 2 v2 squared equals b1. Let's go back and have a look at that was the speed at v is 8. V is 8.60. Half times 8.60 squared minus 9.8 times 1.8 times cos 25. Okay, so 0.5 times 8.6 squared minus 9.8 times 1.8 cos 25 equals 20.99 divided by v squared is 13.99. If I square root that, answer I get 3.74. So v2 equals 3.74 meters per second. Okay, question 3. So, fixed points A and B lie on the greatest slope of a smooth inclined plane with B higher than A. So B being up here, A being down here. The horizontal distance from A to B is 2.4, and the vertical distance is 0.7. Then there is this other point C up there, which is 2.5. A light elastic string of natural length 2.2. So L0 is 2.2. Let's attach one end C, another end to a block of mass 9 kilograms. So there's a tension there, and there's a weight there of 9 kilograms, so 9g. It's smooth. The block is in equilibrium when it is shown at A. So smooth, no friction. Show that the modulus of elasticity is such and such. So if we here, we obviously need some angles. Just trying to think whether there's an easier way or a harder way of doing this. Not sure. Okay, I think we're going to pick that angle as alpha, and then I'm going to pick that whole angle, which might be a mistake, but we'll go with that as beta. So I'm going to resolve T vertically, and so I'm going to say that T sine beta we've got another force here, haven't we? Of course. Got a reaction force here. Okay, so there we go. We've now got proper forces on. So we've gone that is your alpha, so T sine beta plus R cos alpha minus 9g equals 0. And then horizontally we've got T cos beta has got to equal R sine alpha. Okay, there we go. So why did I spot the R? Well, one, because I seem to have just one force going horizontally, so you need, if it's going to stay there, you need something holding it back. So what's going to hold it back? Well, there's no friction, therefore it's got to be the reaction. Okay, so we want to find out the modulus of elasticity. Well, that's in the T. So we want to eliminate the R. Okay, so R, let's put it in there. So we've got a formula here. T brackets sine beta plus R is T cos beta sine alpha times cos alpha. And that equals 9g. Well, these are all things that I can work out. And T is lambda x, well, we can work out what the extension is because we can over L, which is 2.2. We can work out sine beta. So we need to do a little bit less. It's a bit smaller, so we can have a look at this. So let's work out some diagonal lengths on here by a bit of Pythagoras. So the square root of 2.4 squared plus 0.7 squared is 2.5 along there. And let's do this one. So that's 3.2 square root of 3.2 squared plus 2.4 squared is 4. So the extension of there is 1.8. So let's times 1.8 in here. So now we can do sine beta. Sine beta is the opposite, which is 3.2 over the hypotenuse, which is 4, plus cos beta. Cos beta is the adjacent over the hypotenuse, times effectively times cot, which is the adjacent over the opposite, which is the adjacent, which is 2.4 over the opposite, which is 0.7. So sine is opposite, yeah, adjacent, and then the hypotenuse cancel if you're thinking like that. Okay, equals 9g. So this should all work out if we plug that all into our calculator. So 9 times 9.8 times 2.2 divided by 1.8 divided by 3.2 divided by 4 plus 2.4 squared divided by 2.8, 4 times 0.7, close brackets, equals, and hey presto, lambda equals 37.73, which is encouraging. It means we're on the right track. Okay, the block, so that's part 1. Let's have a go at part 2 up here. The block starts at rest and a constant force of 18 newtons acting in the direction of AB is then applied to the block so that it slides along the line AB. Find the magnitude and direction of the acceleration when it leaves point A. So when it leaves, the net force on it is just the force that you're applying, which is the 18 newtons. Okay, there's no other force because it's in equilibrium at that point otherwise. So force F equals ma. So A equals 2, and it wants to find out the direction in the direction A to B. Okay. Okay, that's one of the easiest couple of marks that you'll get. B is slightly trickier because it's now gone all the way up to the top, so it's now at B. So we've got to just look at what's happening to to the particle, so I'm going to kind of redraw it. It's now directly under here. It's 2.5, so there's still a tension up there, and my x is now 0.3. And so this is B. But there is still a force being provided in this direction, which is 18 newtons, and that is at an angle of alpha to the horizontal because it's parallel to the slope. And it's slightly confusing, and of course we've got the weight down, so we've got 9g down. So the magnitude and direction of this let's first of all work out the tension. So the tension equals lambda x over L. So the tension is 5.145 newtons. And we've also got, of course, we've got a reaction perpendicular to this. So I think we've got to split it again. The reaction is perpendicular to the slope, so that's my alpha. So I think I can just go and say well, in fact, R is going to keep, R is perpendicular, so R is going to make sure that it's balanced, because it's not going to fly through the floor and it's not going to fly off the surface. So actually our acceleration, if we just look parallel to the slope, is t sine alpha plus 18 equals 9 and a bit of weight, sorry, minus 9g sine alpha equals 9a. So t times sine alpha, and sine alpha is opposite 0.7 divided by 2.5 plus 18 minus 9 times 9.8 times sine alpha again, 0.7 divided by 2 divided by 9 is minus 0.584 to 3 significant figures, meters per second squared. So acceleration, the magnitude A is 0.584 in B to A direction. Okay, nearly there. We want 3. What is the speed when it reaches B? Well, clearly we can't use suvat because the acceleration is not constant, because we've just shown the two accelerations. So therefore we've got to use energy. So energy at A. Well, there is elastic potential energy, and let's call GPE 0. So we'll say 0 plus the elastic potential energy, which is a half lambda over 2.2 x squared, which is 1.8 squared. Okay, energy at B is 0.7 G times M, which is 9. That's your MGH. Plus, we've got a little bit of elastic potential energy there, times 37.73. Times, was it 0.3 squared? Yeah, we've got the 0.3 we can see from up there. And now, can we equate those? That's the big question. And the answer is no, we can't, because there is an external force going on. So what can we do? Well, we can say that the energy at the beginning, which is a half times 37.73 over 2.2 times 1.8 squared, plus the energy we put into the system. So we're putting in an energy of a force times the distance that that's applied over, which is applied over 2.5 meters, equals the energy that we've got at the end, which is the gravitational potential plus the elastic that we've still got at the end. Let's see, half times 37.3 over 2.2, 0.3 squared. Plus, of course, the thing that we want to know, which is the half mv squared. Plus a half mv squared. So, now it's a case of plugging that all into the calculator. 0.5 times 37.73 divided by 2.2 times 1.8 squared. 27.783 plus 18 times 2.5 is 45 minus 0.7 times 9.8 times 9 that's the gravitational, minus the elastic at the end, which is 0.7715 equals half mv squared. So that's all, add all those up. 783 plus 45 minus 61 minus equals times by 2 divided by 9 square root. V equals 1.51 meters per second. There we go, there is question 3. Okay, and then on to question 4. The region is bounded by the x-axis, the y-axis, and the curve y equals e to the x. So let's just draw that. So e to the minus x is that, and the line x equals k, so that's k, and we've got this region here, so when x is 0, e to the 0 is 1, and the region R, this is the region R, is rotated 2 pi radians about the x-axis. Here's the x-axis, so we're going kind of round here. To find the x-coordinate, the centre mass of the solid, and show how it can be written in the form that. Okay, so first of all we want to find the volume. Okay, so that's my delta x, that's my height y, and that's my distance x. So my volume equals my integral between 0 and k of, imagine this going round, so that's my r squared, is my pi y squared dx. Okay, and therefore my centre of mass is x bar times the total volume, which I'm just going to have confidence that I'm going to be able to work out all right. And that's got to equal the sum of all my centre of masses. So that's going to equal the integral between 0 and k of each one of those separate disks and their centre of mass. So that's x times pi y squared dx. And we times it by a density factor that goes out in both of them, so we're not going to worry about that. So x bar and the pi's go, so we don't need to worry about that. Y squared, so we know that y equals e to the minus x, so we've got the integral of e to the minus 2x minus 2x dx equals the integral between 0 and k of x e to the minus 2x dx. It's both integrals that I feel reasonably comfortable. Obviously the one on the right is slightly more tricky, but hey-ho, x bar is minus a half, or I'm going to swap the limits around for the minus. So I'm going to get times a half e to the minus 2x. I'm going to swap the limits around rather than put the minus in. Equals okay. Oh, I didn't swap the limits around, I said it and then I didn't do it. 0. Okay. Equals, well, this is going to be by parts, so however you do your parts, x over 2 e to the minus 2x with a minus, and then we're going to put that, I know I'm inconsistent, I haven't swapped the limits of that, minus, but I know there's going to be a minus minus, so we'll change that to a plus, the integral of 1, and we've got a half here, e to the minus 2x dx. So we can be a little bit clever here and cross out all those halves. So we've still got x bar. I can probably work this out now. Put 0 in, get 1 minus e to the minus 2k equals, well, let's put k in, minus k e to the minus 2k, put 0 in, I get nothing, okay, plus, this is still between 0 and k, the integral of this, which gives me another half, and another minus, so minus a half e to the minus 2x between 0 and k. Alright, let's give ourselves some more space. So, x bar, 1 minus e to the minus 2k, it's kind of looking hopeful, minus k e to the minus 2k, put k in first, minus a half e to the minus 2k, minus minus, so plus a half. Okay, well that's good. I've got my half there, but I want to do some dividing here, so how are we going to do this? So let's just write it and then we'll see whether we can spot anything nice to do. Minus k e to the minus 2k minus a half e to the minus 2k plus a half over minus e to the minus 2k. Well, it suggests that I want e to the 2k, so what I'm going to do is I'm going to multiply everything by, top and bottom, by e to the 2k. So that becomes minus k, that becomes minus a half, that becomes plus a half e to the 2k over e to the 2k minus 1. So then we've got, on the top, we've got a half e to the 2k minus 1 minus k all over e to the 2k minus 1. There we go. And finally, so back equals, well, we've now got a half minus k over e to the 2k minus 1. Okay, 7 marks, but made us work for it. Okay, part 2. The solid shown in part 1 is placed with its larger circular face in contact with a rough plane inclined at 60 degrees to the horizontal. So 60 degrees to the horizontal is quite steep. So I'm going to make sure that it looks kind of more than 45, just so that my sketch has that, and the larger face, so there, and I know that that distance there is 1, and I know that if it's going to topple, then the centre of mass, the distance from there to the centre of mass, now that is where we measured it from, isn't it? Yeah. The distance there, so whatever x is, and that. So the key is, what is this angle here? And the thing is, we know that that angle must be 60. We know that this line must be vertical, therefore this one is 30 degrees. And if that one is 30, then we know that tan 30 is x over 1. So x is tan 30, which is 0.577. So, if the centre of mass is further along than x, then it will topple. But we know the centre of mass, x bar, equals a half minus k over e to the 2k minus 1. So if we know that k is positive, if k is positive, then e to the 2k is always bigger than 1, e to the power, so this is bigger than 1. So this is positive and this is positive. So as k is greater than 0, k over e to the 2k minus 1 is greater than 0. Therefore x bar is always less than a half, which is less than 0.577, therefore will not ever topple, even at 60 degrees. Okay, now you think that's enough marks for this question, but no, they want us to keep going. And they're then thinking a uniform lamina occupies the region R, find in terms of K. So we're going back to the very beginning question, but we're now doing a lamina just of that region. And we know that that's K, y equals e to the minus x. That's 1. And we want the centre of mass of the lamina. So it's a very similar bit of maths, except we haven't got all the pi's in there. So we want the coordinates x and y. Oh, okay. So we'll do it in terms of this strip. So x bar times the area, which is the integral between 0 and k of area is y dx. Just add up all those rectangles. Equals the x bar of all of those individually. So x, y, dx times a constant, but we don't worry about that. The integral between 0 and k. So x bar equals the integral 0 to k e to the minus x dx, integral 0 to k x e to the minus x dx. This feels very familiar. Okay, and maybe we can do it a bit quicker, but it's still giving us 7 marks, so we'll go equals pi, equals the integral there, the minus e to the minus x, so I'll switch these as I did last time. Equals, by parts again, it's pretty dull, x e to the minus x with a minus, so let's switch these, minus, put the plus, the integral between 0 and k, x is 1, e to the minus x dx, x bar, 1 in first, minus e to the minus k equals, let's put this in 0 goes, so we get minus k e to the minus k. Plus, this is going to be minus, so we'll just go e to the minus x, and we'll swap these over k and 0. Okay, this is just x bar 1 minus e to the minus k equals minus k e to the minus k plus 0 in is 1 minus e to the minus k. X bar equals, start with a positive, 1 minus e to the minus k to the minus k all over 1 minus e to the minus k. And it doesn't ask me to simplify, so I am not going to spend any time simplifying that. Okay, and then we've got to do the same thing for y. So I'm now thoroughly bored because it is pretty much the same question again, but I've just got to keep my wits about me. I'm going to use the same strip. That's 1 dx y equals e to the minus x, that's k, 0, that's x. I'm going to integrate y bar times the volume, which is the integral between 0 and k of y dx, and that's got to equal the integral between 0 and k of y over 2 because that height's y over 2 times y dx. Okay, so that's our only little difference. Is the midpoints of those are the centre of mass in the y direction, if we're thinking in the y direction. So we've got each one of those, and we've got the overall centre of mass in the y direction times the volume. So this we've already done, so we can kind of just go back and have a look at this. So y bar sure I didn't cancel anything there, is 1 minus e to the minus k equals y squared over 2, so we've got a half, we'll take out the integral of e to the minus 2 x dx. Okay. But that is a bit nicer, equals 0, okay, equals, I think we can just go straight to square brackets, a half with a quarter taken out and a minus, so that's going to be e to the minus 2x, and we'll swap the limits around because of the minus, so that equals a quarter. Put the 0 in first, 1 minus e to the minus 2k. So our y bar equals 1 minus e to the minus 2k over 4, 1 minus e to the minus k. Done.